Welcome. This is the Cisco CCNA ENSA, also known as the Enterprise Networking Security and Automation course. This course focuses on the CCNA version 7 curriculum. This is course 3 of 3. Alright, moving on, we have our different types of hardware. We have our switching and we have our routing hardware. First, we're going to talk about switching hardware. Switches comes in a multiple layers of platforms. They come with multiple port densities. They come with multiple add-on slots. Here we have, I believe these are GBICs or SFP connectors. Here we may have HDMI connectors or special link connectors. We have USBs, but those aren't really for our additional types of ports. You'll also notice that we have port densities. This port is a 24 port. This port is a 48 port. So they are different. They could also be certain ports cover certain technologies where some ports don't. So the issue is our switches are not always created equal. However, more commonly than not, the height of these units, the height, is typically going to be a 1U based unit. So the form factor, for example, the height and the width typically are going to be the universal standard 1U. However, that's not always the case, so do keep that in mind. So to ensure you have the appropriate device, we need to understand the requirements of the network. That allows us to purchase the appropriate switch. So our platforms can be all over the place. Here we have a Meraki Cloud Managed switch, and this does allow for virtual stacking instead of hardware stacking. So this will do it over traditional LAN networks as opposed to having a separate cable to do it. At the bottom, you're going to see different types of Nexus platforms. These are also possible switches, but these are not 1U switches. Like this is, I believe, a 3U switch. And there are other ones out there. Some of them are like a 5 or 8U level switch or greater. Again, it all depends on your requirements. Realistically, these larger switch units are not cheap. I've been able to purchase like a $200,000+ switch because that's what was needed for the organization. However, most organizations aren't going to be able to splurge on that. So there's pros and cons for picking out the different types of switches. Meraki is now owned by Cisco, so you're going to start seeing more Meraki-based products in the Cisco portfolio. Again, service providers will have additional layer switches. These are going to be that help run a service network or like an ISP, way outside the scope of what an average everyday type individual would be using. They will require very specific intelligence application features. They're going to need unified services, virtualization. They're going to have integrated security. And they're going to have to be able to have more of a simplified management for this environment. The issue here is a regular core switch or a regular distribution switch and a ISP level switch. They're not going to be the same. All this is supposed to point out is that there are different platforms. There's different levels of these switches, and it all depends on your needs. Different form factors. Typically, 1U is the more common. However, we can get different switches and different form factors that are either fixed or more modular or stackable or non-stackable based off of your requirements. Stackable basically means you can have these 4 switches and there's a cable in the back that connects them. And that way, all these switches can logically act as one type of switch, when in reality, it isn't. And we see that by using switching cables. And you'll also notice they have dual power supplies. Power supply and power supply. You can also do redundant power supplies. Again, most of these are going to be 1U, and that's going to be the traditional 1.75 inches in height. Each of these interconnections will use a special cable, and that allows these switches to stack. So one of the things that I'd said earlier was this concept of port density. And port density essentially is how many ports the switch can handle. If we have the ability to stack 4 switches, and these are 4 48-port switches, well, that's how many ports we can have. If we need more than that, we may need to have a different chassis. This one can have all of the individual cards filled up. This right here is a management card. This is a management card. They're redundant management controllers. And this guy right here is some form of fiber or SFP type connector. Well, we could replace the fiber with another 48-port switchblade, and we could replace the second controller with a 48-port switchblade. So again, it can grow based off of the user requirements. And as it grows, basically we're talking about port density. How many ports are there? So how do we calculate the cost of a unit? We base the cost off of an additional port. If we wanted to add an additional 48-port switch, we could do that based off of the port cost. We can calculate the additional cost of the switch divided by how many ports we have, and we can figure out the appropriate cost per port. And that way we can justify the additional cost based off of the individual port cost. Each switch will have what's called a forwarding rate. How much data can it actually forward? How much data can it process? So switch products lines are classified by forwarding rates. Entry-level switches have lower forwarding rates than higher-level switches. Again, normally if we're talking an entry-level switch may have 24 ports or 48 ports. Well, they're going to be limited to how much they can forward based off of how many ports they have. A ISP level switch, because of, again, the increased amount of port density, has to have additional resources to be able to manage all of those, so they have a much higher forwarding rate because they can have additional ports. Port rates or data rates are typically measured in megabits, gigabits, 10 gig, 100 gig, or more. Access layer switches typically do not need the operating at the full wired speed because they're physically limited basically by their uplink. They may have one uplink of a gigabit. Well, if they have 24 10100 connections, well, realistically, if they have 24 100 megabit connections, if the switch is operating at 100% capacity, it's going to be able to process 2.4 gigabits per second on that local switch. However, the local uplink might only be a 1 gig uplink. So you may have 2.4 gigabits worth of data being able to be transmitted, but if you're limited by the uplink of 1 gig, you're limited at that data rate. One thing that the switch provides that is actually extremely important is the concept of PoE, Power over Ethernet. The switches have the ability to power devices over a switch port. Now again, not everything can be powered this way. Normally phones, access points, cameras, those can be powered over our PoE. PoE basically takes an Ethernet cable and it puts power on a pair. And that power powers those devices. That way you don't need additional power outlets. If you're mounting an access point on the ceiling, you don't need power ran to that location because the access point can get its power through the switching fabric. However, that means that fabric must support PoE. must support the Power over Ethernet. And there are different flavors of PoE, so also keep that in mind. It's not just all PoE is functioning. PoE has been around for quite a while now, so there are different versions of PoE. PoE versus PoE plus versus PoE plus plus. And there's different standards in how much power that each PoE can support. Some support 24 volts, some support 48 volts. So those are considerations. However, PoE is actually not really covered in that level of detail for the CCNA. So just wanted to point that out. We also have different layers of operational switches. Switches can operate at layer 2, or if you have a specialized switch, they can operate at layer 3. Normally, multi-layer switches that operate at both layer 2 and layer 3, they will support specialized hardware such as application-specific integrated circuits, ASICs. Basically, this is dedicated software and dedicated software structures that can streamline forwarding of packets specifically to the processor. That way, there could be specific functionality for those switches. Maybe that switch specialized in having a VoIP controller. That way, it handles voice over IP a little better than an average everyday switch. So overall, how do we pick the right switch? How do we pick a switch that's going to provide the same function that we're going to need? Well, first, we need to understand the cost, the budget we have to work with. That allows us to pick out features like port density, power, port speeds, how scalable it is it stackable, how reliable is it, and things of that nature. These are the key considerations when selecting a switch. So now that we talked about switches, we can talk about routers. So router hardware. So routers use the network portion, normally a prefix of the destination address, to properly select the destination. So if a link goes down, an alternate path should become available. All hosts on the network will specify the IP address of the local router's interface as a default gateway. We already know that. We understand how default gateways work. We understand that the interfaces can be a physical interface or a virtual interface. Routers contain broadcast domains. A router is a layer 3 device and it functions at layer 3. They normally interconnect geographical separated areas. Realistically, they connect one LAN to another LAN. They group users logically by department, by application, by company, by resource, by certain criteria, whatever that may be. They provide enhanced security by filtering or controlling the flow of data packets. A Cisco router, here is an example of an ISR, or Integrated Service Router 4000 series. We've been working with 4331s inside of multiple labs, and these are pretty common. They're optimized that work at the branch level. Just like our discussion on switching technology, our routers are going to be the exact same thing. Our routers can have a 1U chassis router, or it can have an 18U chassis router, or anything in between. These are called aggregation service routers, ASRs. Here we're looking at the ASR 9000. And sometimes you can have an open door or closed door. All of these are about network convergence systems. These normally operate at the service providers. These are routers for the service providers' networks. And they help provide end-to-end solutions. Normally these are like multi-million-dollar devices. Maybe not multi-million, but I mean, I've easily seen one of these cost well over $1 million. We have add-ons, because as our connections come into our routers, we may have different types of inputs that are required. So industrial routers, such as the ones shown below, they could be the Cisco the 1100, it could be a home router, it could be a dial-up router. It just really depends on what we need. We have router form factors that are small. That could be less than 1U. This is going to be a Cisco 900 series. This is a fairly small. This is more equivalent to like a Soho or a small office home router. We have large routers, again, the Cisco ASR 9000 or 1000 aggregate service routers. These are huge port density, port dense, very resilient, very programmable, very scalable type devices, but you're paying for them. Here's another example. It can have a multi-power supplied unit with multi-routable ports. This is a converged system. It's a 5500 series router with multiple ports. Again, this is typically going to be used for like a data center or large network or an ISP. This is going to be something smaller than a Cisco 900. We have a Cisco 800, and this is definitely a specialized unit. This router is designed to be small and to be used outside. This is made to be operating in a very harsh environment. So again, all the devices operate different levels based off of the requirements. They scale and they grow based off of those requirements. And that is it for this module. If you got any questions or concerns, please reach out. Thank you.